You probably have a friend, or maybe you are that friend, who buys a $2 office raffle ticket, like, every single Friday.
Oh, yeah. We all know one.
Right. And if you ask them why they do it, they'll usually swear that eventually they're due for a win. They're looking at this one upcoming Friday, just hoping it's the one.
Which is, I mean, it's entirely human to look at it that way.
Yeah.
We tend to hyper-focus on the immediate event.
Mm-hmm.
But mathematically, the real question isn't whether this particular Friday or, even next Friday is the lucky one.
Right. Because any single ticket is just sort of noise.
Exactly. The actual question you want to ask is, what happens over a whole year of Fridays? Like, what do you get back, on average, per ticket?
Okay, so you're looking at the typical week, repeated over and over, just stretched out over time.
That's it. And that long-run average return over many tries is the core of what we're looking at today. It's a concept called the expected value. Simply put, it's the long-run average of a random outcome.
Well, let me stop you there, because when you say average outcome, my mind goes in a few different directions.
Yeah.
Like, what exactly are we averaging? Are we averaging the literal dollars, the number of tickets?
Think about it as running the exact same random experiment thousands of times.
Okay.
You sit there, you run the experiment, and you write down every single result on a long sheet of paper. The expected value is just the number that all of those results eventually settle around when you average them together.
Okay, let's ground this a bit. I want the absolute simplest case we can think of. So, say I take a fair six-sided die, and I roll it over and over, and I average all the numbers that come up. Intuitively, I'd think the average lands somewhere, right in the middle.
It does. If you average the numbers 1 through 6, it lands exactly on 3.5.
But wait, a six-sided die can never actually show a 3.5.
Right.
I mean, I can roll a 3 or I can roll a 4. There's no 3.5 side. So how can we call that the expected value if I can't ever expect to get it?
That is precisely where people often get tripped up.
Yeah.
The expected value, or the mean, isn't a prediction of any single roll.
Okay.
It's the exact value that the average of many rolls approaches. It really doesn't have to be a value you can actually hold in your hand or land on in a single try.
So it's more like a destination.
Exactly.
But I want to visualize where that 3.5 actually comes from, because mechanically you're adding 1, 2, 3, 4, 5, and 6, and then dividing by 6.
Yes, but let's step away from the raw arithmetic for a second and try a physical analogy. Picture a standard wooden ruler.
Okay, got it.
Now picture each face of that die as an equal heavy iron weight sitting on that ruler.
So 1 through 6.
Right. You place a weight at the 1-inch mark, the 2-inch mark, all the way down to 6. If you try to balance that ruler on your finger, the expected value, that 3.5, is the dead center balance point.
Okay, I can see that clearly.
Yeah.
Since it's a fair die, all 6 weights are exactly equal, so it balances perfectly in the middle. But what happens if the die is loaded? Like an unfair die where there's a 95% chance of rolling a 6 and almost nothing for the rest of the numbers.
Well, imagine that same ruler. Now you take almost all of that heavy iron weight and you pile it squarely onto the 6.
Oh, right.
That heavy mass on one end drags the balance point all the way over. It slides exactly to 5.85.
5.85.
Yeah. It's still a balance point, but it's a weighted average. Each value pulls on the balance point based on how likely it is to occur.
Okay, so if we need to write this down, like formalize it, what is the actual mathematical definition of this balance point?
There are two versions, depending on what you're measuring, but they are the exact same underlying idea. If your variable is discrete, meaning separate, countable things like die rolls the mean is written as mu sub x, or e of x.
Mu sub x or e of x.
Right, and it's simply the sum of each value times its probability.
So for the discrete version, you multiply every possible outcome by its chance of happening, and you add all those separate pieces up. And just to be completely clear, when we say mu sub x and e of x, are those terms like completely interchangeable?
Completely interchangeable.
Yeah.
Same number, two different names. Mu sub x is the mean. E of x is the expected value. You'll see statisticians swap between them depending on the context.
All right, I want to test this discrete formula. Let's say you're an inspector on an assembly line.
Okay.
And you have a batch of 8 components. 5 of them are perfectly good and 3 are defective. You randomly grab a sample of 3 components. Let x be the number of good components in your hand.
That's a perfect scenario.
Yeah.
So your variable x could be 0 good components, 1, 2, or 3 good components.
Right.
Now, if we run the probability calculations for that sample, the chances work out like this. The probability of getting 0 is 1/56.
Okay.
Getting 1 is 15/56. Getting 2 is 3056. And getting 3 is 1056.
Okay, let me visualize those probabilities. If I build a bar chart in my head, the tallest bar is definitely at 2, since that has a probability of 3056.
Mm-hmm.
That's more than half the time. So the balance point, our expected value, has to be somewhere near 2. Probably just a little under it because the weight is pulling slightly toward the lower numbers.
Your intuition is tracking exactly right. If we calculate E of x, we use our definition.
Yeah.
The sum of each value times its probability.
Right.
So we take 0 times 1/56 plus 1 times 15/56 plus 2 times 30/56 plus 3 times 10/56.
Got it.
That gives us 105 over 56.
Let me simplify that. Both divide by 7, so that simplifies to 15/8, which is exactly 1.875.
Exactly. So on average, if you repeated this inspection process thousands of times, you'd average 1.875 good components per sample.
Okay, that makes perfect sense when we're counting physical, separate things like individual components or die rolls. But what happens when the variable isn't neatly separated into 1, 2, or 3?
Like a continuous variable.
Yeah, what if we're measuring something fluid, like time?
Well, that takes us to the continuous version of the definition. When you move to a continuous curve where there are infinite tiny fractions of a possibility, you can't just add up separate discrete blocks anymore.
Right, because there's no gaps.
Exactly. You have to find the total area under that curve.
Yeah.
So that discrete sum transforms into an integral. The expected value becomes the integral of x times f of x.
Okay, let's apply that. Say we're looking at the lifetime of a generic electronic device.
Good. Imagine its lifetime, measured in hours, follows a specific continuous density curve. Let's call the time z. The density is 2/7 times e to the power of negative 2z's over 7.
Okay. If I picture a curve with a negative exponent like that, it starts high on the left and then decays as time goes on, trailing off with a long tail to the right.
Yes, exactly.
So that tells me most of these devices fail fairly early, but a small handful of them manage to last a really, really long time.
That's exactly what the shape means. Now, to find the mean lifetime, we use the continuous formula. We take the integral from 0 to infinity of the time times its density. And when you run that integral, it results in 7/2, or 3.5 hours.
7/2, 3.5 hours. Wait, if I think about the shape of that curve, it starts high at 0 and just drops.
Yeah.
The absolute tallest point, the most common time to fail, is way over on the left.
Right at the start.
But the mean is sitting at 3.5, which is out to the right of that peak.
It is. And that's a fascinating feature of skewed distributions. Because of that long tail of rare, long-lived devices, those few incredibly stubborn devices act as heavyweights far down the ruler.
Oh, I see.
They're heavy enough to drag the mean to the right of the peak. It's the exact same weighting concept we saw with the loaded die, just mapped onto a continuous curve.
So we've been averaging the exact thing we're measuring, right? The hours, the components, but what if I care about something derived from that, like the financial cost of those hours or a specific payout?
Okay.
I don't want the expected value of x. I want the expected value of some function built from x. Let's call it g of x.
Well, you don't need a new process for that. You use the exact same machinery. If you want the expected value of a new function, g of x, you simply weight g of each value by its probability and add them up.
Right.
E of g of x is just the sum of g of x times f of x.
Let me make sure I follow. If I have an expression like x squared minus 3x, I don't need to, learn a whole new definition.
No, man.
I'll just swap that expression right into the weighted sum. For each possible outcome, I compute x squared minus 3x, multiply it by the probability of that outcome, and add them all together.
You have it perfectly. You just feed a different function through the exact same weighting machine.
Okay, but please tell me there's a shortcut. If I have a complex formula or two different variables, I do not want to be running those full sums or integrals from scratch every single time.
Oh, there is a shortcut, and it's incredibly useful. It's called linearity.
Linearity, okay.
The rule is simply that e of x plus or minus by equals a times e of x plus or minus b times e of y. And the expected value of a constant c is just that constant c.
So just dictating the formula is one thing, but why does that actually work?
Think about it intuitively. Say you have a job inspecting those components we talked about earlier.
Okay.
You get a base pay of $50 a day, plus $5 for every good component you inspect.
Yeah.
Your pay is a linear function of the components.
Right.
You don't need to build a massive new probability tree to figure out your average pay. You just find the average number of good components, multiply that by $5, and add your $50 base pay. Constants pull straight out, and some split apart.
That is elegant.
Okay,
Let me test this live with a slightly messier example to make sure the mechanics work.
go for it.
Say the mean of x, mu sub x, is 3.1, and the mean of y, mu sub y, is negative 1.2.
Okay.
And let's define a new variable z as 2x minus 3y. I want to find the expected value of z.
Walk me through your calculation using linearity.
Okay, since sums split apart and constants pull out, I can just evaluate the pieces. 2 times the expected value of x, 2 times 3.1 is 6.2. Then we subtract 3 times the expected value of y. So subtract 3 times negative 1.2. Subtracting a negative is like adding, so that's adding 3.6.
Exactly.
Finally, 6.2 plus 3.6 equals exactly 9.8.
Precisely 9.8. And here's why that's so powerful.
Yeah.
This elegantly works, even if x and y are related to each other.
Really?
Yeah. You don't have to worry about how they interact beneath the surface. You can just break the expectation apart.
Wow, okay. So what does this all mean when we loop back to the very beginning? My friend and his weekly $2 raffle ticket.
It means we can reframe his habit purely mathematically. Think of any game's payout as a random variable, x.
Okay.
That's the dollars you win, which is a positive number, or the dollars you lose, which is a negative number. By the law of large numbers, your average payout per play approaches E of x as you keep playing.
So E of x is the long-run payout.
Yes, and that gives us a very clear objective test for fairness. A game is mathematically fair when E of x is exactly 0. Over the long run, you neither win or lose. If E of x is positive, the game favors the player. If it's negative, it favors the house.
Which means every single game in a casino is, by design, safely sitting in the negative.
Always. If it wasn't, the casino wouldn't exist.
I want to test this fairness idea with a fast, concrete game.
Okay.
If I sit you down at a table and offer you a simple coin flip, you win $1 on heads and you lose $2 on tails.
All right, let's run the expected value for a fair coin.
Okay, heads and tails are a 50-50 chance. So the expected value is 1/2 times $1 plus 1/2 times negative $2.
Right.
Half of 1 is 50 cents. Half of negative 2 is negative $1. 50 cents minus $1 equals negative 50 cents.
Yep.
So on average, I lose $0.50 every single time I play. That is definitely a losing game.
It is. But let's flip the premise. What chance of heads would actually make this game fair? Let's call that unknown probability of heads P.
Okay, let me think. To make it fair, I need to force the expected value to equal 0 and solve for P. The probability of heads is P, and the probability of tails is 1 minus P. So P times 1 plus 1 minus T times negative 2 equals 0. Let's distribute that negative 2. P minus 2 plus 2P equals 0. 3P minus 2 equals 0. 3P equals 2. So P is 2/3.
Exactly. You would need a biased coin that lands on heads exactly 2/3 of the time just to break even on those rules.
Let's try something slightly more complex where the probabilities aren't just a simple coin. Give me a card game.
Okay, let's use a standard 52-card deck.
Uh-huh.
You draw one single card. Here are the payout rules. You're paid $7 on an ace, a 6, or a king.
Okay.
You paid $11 on a 7, a 5, or a 3. And you lose on anything else.
Okay, I need to map out the fractions here. An ace, a 6, or a king. But wait, there are 4 suits in a deck.
Right.
Hearts, diamonds, clubs, spades. So naming a rank really names 4 specific cards. 3 ranks that pay $7 means 3 times 4, which is 12 cards. So the probability of a $7 win is 12 50-seconds. The $11 payout is for a 7, a 5, or a 3. That's also 3 ranks. 3 times 4 suits is another 12 cards, so that probability is also 12 50-seconds.
Yep.
We've accounted for 24 cards out of 52. That means the remaining 28 cards are losers. So the probability of losing is 28 50-seconds.
You have the probabilities mapped out perfectly.
Yeah.
12 50-seconds, 12 50-seconds, and 28 50-seconds.
No.
Now, here's the ultimate question. What should a player pay as a stake to make this game perfectly fair?
As a stake.
Right. Remember, you only forfeit your stake when you draw a losing card.
Okay, to make it perfectly fair, the game's expected value has to be 0. That means the expected winnings have to exactly balance out the expected loss of the stake.
Exactly.
Let me set up the math. The expected winnings are $7 times 12 50-seconds plus $11 times 12 50-seconds, and that must equal the stake times 28 50-seconds.
Take your time with the calculation.
7 times 12 is 84. 11 times 12 is 132. 84 plus 132 is 216.
Hmm.
So my expected winning side is 216 over 52. That equals the stake times 28 over 52. The 50 seconds are on both sides, so they cancel out completely. The stake equals 216 over 28.
And if you divide 216 by 28, it comes out to about $7.71.
$7.71. When you just say that number, it feels surprisingly high for a simple card draw.
It does.
But when I look at the probabilities, I realize that losing is actually the most likely single outcome. 28 out of 52 cards are losers. That's more than half the deck.
Right.
So the fair price has to be that high because the wins, when they do happen, pay out $7 or $11, which pulls the mean up even though you lose more often than you win.
That's the intuition we're building toward. You're balancing the heavy frequency of losing against the weight of the positive payouts.
This has really clarified things. Let me concisely tie the session together for the listener. There is really one central idea running through all of this, the weighted average.
Yes.
E of x is just the sum of each value times its probability. Linearity provides a clean shortcut so we don't have to start from scratch every time we combine variables. And the fair game test is simply setting E of x to 0.
That summarizes the mechanics entirely.
Mm.
Everything we discussed today, from the ruler to the card game, was focused on finding the center of a distribution.
But there is a limitation there, isn't there? You could have two distributions that share the exact same mean, the exact same expected value, but look completely different in reality.
How so?
Well, one could be tightly clustered right around that mean, and the other could be wildly scattered with massive extremes in both directions.
That's a great observation, and it's exactly what comes next in Lecture 8. We'll look at variance, spread, covariance, and how to combine variables. We'll move from finding the center to measuring how far things scatter away from it.
But before we wrap up, I want to leave you with a brief thought to mull over. Let's say you're offered a game with a positive expected value.
Okay.
Mathematically, the rules say you should always play. It favors you in the long run. But what if the short run of that game includes a 99% chance of going totally bankrupt before you ever hit that long run average? If my friend's $2 raffle tickets suddenly cost $2,000 a week, the expected value ratio might technically be the same, but the reality of playing it changes completely. It reframes expected value not just as a math problem, but as a question of what kind of risk you can afford to survive.